Right, the recording has started, Johan. You welcome to carry on.
Okay, I've unmuted, so hopefully everybody can hear me. Welcome to chapter 21 this evening. And I hope you learned something more for your exam to prepare yourselves. Tonight's lecture is all about modulation. As I said last time, we're busy building all the puzzle pieces together, and we're now starting with the nice stuff so that you can start building radios soon. Okay, what is modulation? Modulation is basically when I capture the information that I want to transfer onto my radio waves. In other words, when I've got a cell phone and I'm busy talking with my cell phone, my voice is the information that I need to capture on top of the radio frequency that is transferring it from my cell phone to my tower and onto the internet to the next tower to the next cell phone. So that's all modulation is. It's the information that I'm putting on top of a carrier frequency. And I can do that in different ways. The first one is I can change the carrier frequency's time, and we'll show you how we do that. We can change the carrier frequency's amplitude, and we'll show you how to do that. We can also change the carrier frequency's frequency that it is operating or that it is oscillating on. And then we can change the phase of my carrier frequency. I can change that as well. Or I can combine them as above, and we'll get to some examples of a combination of the four things that we can change. And that's pretty much all you can do with a radio wave. You can change the time, the amplitude, the frequency, or the phase. The first one, and this is most probably the oldest one that dates back to way before even the Titanic sank in the North Atlantic Ocean, is what we called continuous wave and frequency shift keying. Okay. CW, continuous wave, all I do is I change the time of my carrier frequency. In other words, I switch it on, I switch it off. I switch it on, I switch it off. But I switch it on and off, obviously, in a certain sequence. And most of you must have heard about Morse code, which is a series of ders and dars, dots or dashes. So I would turn the transmitter on and off for short periods or longer periods of time to coincide with my Morse code characters, dots and dashes. CW, I'm changing the time of the carrier by turning it on and off. The other one which I can do is frequency shift keying. What I do with frequency shift keying is I jump the frequency of my transmitter. In other words, at moment one, and if we look at, where I see Joe is there. If I look at this signal, this represents a logic 0, and we'll still get to digital systems, I think, in September somewhere. This represents a logic 0, this represents a logic 1, or this is not true and that is true. So when my signal is not true or it's a 0, I oscillate at a certain frequency. Let's just take an example, 1 megahertz. I oscillate. The moment my information that I want to transfer becomes a logic 1 or a true value, I jump to 2 megahertz. And when it goes back to a non-true state, I would then go back to 1 megahertz. So I jump between 1 megahertz, 2 megahertz, 1 megahertz, 2 megahertz as my information changes state. Okay. Morse code or CW, I would turn the transmitter on and off as my information changes state from a 0 to a 1 or from non-true to true. Okay, so those are the first two. is continuous wave modulation and frequency shift keying. And they rely on changing the carrier's time. Why are they still used today? People will ask. They are incredibly efficient. All the information that I'm transferring sits in my carrier frequency. And this is a representation of my carrier frequency in the frequency domain. Remember last week we spoke about the time domain and the frequency domain. So this is my carrier frequency in the frequency domain, and you can see it's a nice straight single line going up. So all the energy, all the joules, all the watts that I'm radiating is captured in this small frequency band that I'm transmitting at. I'm not wasting any power. All my power lies here. That's why continuous wave and frequency shift keying is very, very efficient. If it was an FSK signal, this line would jump to, for example, there, and it would jump back. So it would jump continuously between this line and this line, depending on if I'm through or not through. But the line would look exactly the same as the CW line, a single, nice, thin little line. Okay. Next one is amplitude modulation. So I'm changing the amplitude of my carrier frequency. So I've got an audio signal, which is represented by this long sine wave, and I have a carrier frequency, and I change the amplitude of my carrier frequency to represent my analog information or my input information, in this case audio, that I apply to my carrier frequency. Okay. It's a difficult one, and we'll get to it now. If I overmodulate, so in other words, I change the amplitude of my carrier frequency too much, I create distortion and I create harmonics. So if you get the question in the exam paper, when does distortion occur in an amplitude modulated signal? It's when I overmodulate, so I modulate more than 100%. If we listen to normal broadcast stations on shortwave, medium wave that uses amplitude modulation, they typically run with a modulation index of 85 to 95%. So what does that mean? That won't be a straight line here in the middle. There will still be carrier present. So I only modulate, or I change the amplitude by 85 to 95%. Typically, amateur radio used to work around 66% modulation on AM. There's compression techniques that they use to up it, but in the old days, 66% was a good value for amateur radio. Why don't we use it anymore? Because it is wasteful. It's really, if you want to look at fruitless and wasteful expenditure, you look at an AM modulated signal. That is fruitless and wasteful expenditure at its best. Why? Look at my carrier in relation to my sidebands, in other words, my information. 2/3 of my power, of my energy, is wasted in my carrier frequency, and it's doing nothing. It doesn't carry any information. It doesn't have any data. It serves no real purpose in life, but it's wasting 2/3 of my energy, my watts that are going to my antenna. Of the third that remains, the lower sideband and the upper sideband is a mirror of each other. So in other words, the audio signal that is modulated on the upper sideband side and on the lower sideband is the exact mirror of each other. So of the third that's left over, half of it is also wasted, fruitless and wasteful expenditure, because it doesn't add value to my signal. So that's why amplitude modulation is not a very popular method in amateur radio, because it's wasteful. They still use it on shortwave and medium wave because the equipment needed to receive it is so more simplistic, so much easier, so much cheaper to do. That's why they still use it for BBC and Deutsche Welle and all these radio stations you still find on shortwave and medium wave. It's easy to receive. It's not difficult to receive. Upper sideband, lower sideband, you'll see when we do transmitters and receivers, is a bit more complicated, and it needs a bit more hardware to receive. Okay, it's amplitude modulation. So the clever guys came up with another scheme. They thought, how do we get rid of this wasteful expenditure without having an election? They came up with something which they called double sideband suppressed carrier. DSB, SC, you'll see it in your manual. So what they do is they filter out the carrier frequency so that the energy is concentrated on my lower sideband and my upper sideband. But again, it is still wasteful and fruitless expenditure because this sideband is a mirror of this sideband. So half of my energy, although I've reduced the amount lying in my carrier, half of my energy is still wasted because I'm duplicating my information in the lower sideband and the upper sideband. But it is also something that the amateurs did do years ago, and it is in your manual. That's why it's up on the screen for you. Then the most efficient one at the moment for voice is what we call single sideband. So in other words, when I've modulated my carrier frequency, I use electronic hardware to get rid of this one sideband and to get rid of my carrier. So I filter out carrier and I filter out one of the sidebands, and the only thing that goes to my antenna is one of the sidebands, in this case, the upper sideband. So all my energy, so everything that my radio is eating up in terms of power that's going down the coax to the antenna gets radiated if I have a perfect resonating antenna. I've got rid of wasteful and fruitless expenditure. Okay, that's single sideband. Let's just see. I see there's a lot of people. Louis, good evening to you as well. Any questions to this point before I carry on? Nothing. Okay. Just shout if there's anything. I don't always watch the screen with your names on. So you're welcome to stop me if there's questions. Then we're looking at frequency modulation, where we change the frequency of my carrier. So what I do is I've got an audio signal in this case, a nice long wavy audio signal, and I apply it to my carrier frequency by changing the frequency of my carrier. So you can see where my amplitude of the audio reaches a peak, the frequency is high. And as I go down into the trough, where my amplitude of my modulating signal is at a low, my frequency is also at the lowest point it's going to go to. And then as it goes positive again, the frequency goes up to a maximum. And as it goes down again, the frequency goes down with it. So this audio signal is captured in the change of frequency in my modulated signal. Very efficient, and we'll get to that now, but it's very efficient. This is typically in terms of frequency modulation in the frequency domain, what our spectrum looks like. So we've got all these fingers standing up at frequency. So let's say my carrier frequency was, as an example, 100 megahertz. So at 100.1, there's nothing, but at 100.2, there's something, 100.3, there's something, 100.4, 100.5, and then it goes down. So there's energy in each and every one of these frequency components. They all contribute to transferring the information from one radio to the other radio. I don't waste any energy. It's all used up in the frequency components. Okay. Already I can tell you, let's just go back here. If we look at any AM signal, and it's some of the questions that could come from the exam, because we're changing the amplitude, my signal is more prone to interference from interfering stations or interfering devices if I'm amplitude modulating my signal. If I'm frequency modulating my signal, if there's interference, it's less prone to interference. And that's why if you listen to your FM radio in the car, it sounds good because it's like crystal clear. Where if you listen to AM radio, you get the station fading and it's coming back and then it's loud and then it's soft as interference affects the amplitude of my carrier frequency. So if they ask you which one is the least prone to interference in the exam, you know FM. Okay. Then the last one in this batch, we're changing the carrier's phase. Difficult one to grasp, but let's try. Again, I've got information which is represented by true values and not true values, or zeros and ones in this case. Okay. And I need to transfer that information from, for example, my computer to somebody else's computer. And what they do is they use phase shift keying. So in other words, when the modulating signal changes state, so in other words, this stage, it's going from a true value to a not true value, my modulating frequency would stop and it would restart exactly 180 degrees out of phase. Okay, if you look at that signal, you'll see it's jumped 180 degrees. When it changes from a 0 to a 1, my carrier frequency will stop immediately and it will start again 180 degrees out of phase. So if you work this graph out nicely, and you can look at the lecture afterwards again, you'll see every time there's a state change going from a true value to a not true value, or from a 1 to a 0, I stop my carrier and I start it again at a different phase point. And that is why they call it frequency, a phase shift keying, because I shift the phase every time there's a state change. It's very efficient. If I look at the spectrum of a phase shift keying, a PSA signal on the frequency domain, you'll see I've got this typical nice sharp carrier frequency and very little harmonics going down. So again, it's an efficient way without a lot of wasteful and fruitless expenditure going on. I hope that one got home. Then the last one, we said a combination of all of them. Now, this is, cell phones use a method or a form of QAM. Your Wi-Fi uses a form of QAM. But all that quadrature amplitude modulation means is I combine phase modulation with amplitude modulation. So in other words, I can transfer 3 times the amount of information on my carrier frequency than what I would have been able to do if I only use phase shift or I only use amplitude. But because I'm combining amplitude with phase, I can transfer more information instantaneously with a single frequency. So it's difficult to grasp, but if you look at it, my data is represented by 101, and it's changed here to 100. So what happened at this change? I changed the amplitude of the carrier. At this point here, the data changed from 100 to just 1. So what did I do? The amplitude has jumped back, because remember now in this picture that they've drawn here for us, that last one is representing the amplitude change. And this first one is representing the phase change. So if you work this through, you will see that every time there's a change in the data, I either change the phase, or I change the amplitude, or I change both. Okay. So in this case, I only changed one at a time because only one bit changed. But yeah, it starts getting a bit more complicated, and you have to look at the graph carefully. Yeah, I'm changing phase as well as amplitude together at that point. Yeah, the phase changed as well as the amplitude changed. So they've expanded this and they made it bigger and bigger, so you get even more complex QAM methods. But for your manual, for your exam, this is the only one which is important, is every time there's a state change, I change either the the amplitude, or I change the phase, or both. And that is quadrature amplitude modulation. Hope it sank in. I'll leave the graph there for a second to view. If you just want to study it and see if you see the pattern of the data versus the change in modulation. Okay, hopefully as clear as mud. Questions before we move on? Gee, everybody's quiet tonight. Okay. In summary, which is important, some of these things you need to know. We'll get to the questions at the end. You'll see some of these things pop out of those sample questions for the exam. Carrier, if we change the carrier time, CW, FSK, it's very efficient. It's very simple electronics. It uses very little bandwidth, and it's got a high immunity to noise. Okay, high efficiency, simple electronics, low bandwidth, high immunity to noise. If we look at amplitude modulations, either AM, double sideband, or single sideband, it's got a low efficiency, medium electronics, high to low bandwidth. Okay, what does high to low mean? So AM is high and single sideband is low, but it's got a poor immunity to noise. Okay, remember that, poor immunity to noise. Carrier frequency change, FM, it's highly efficient. It's got some complex electronics. It uses a high bandwidth, but it's got an incredibly high immunity to noise or interference. PSK, where we change the phase, it's highly efficient, complex electronics, low bandwidth, and very high immunity to noise. And then the combination of above QAM, it's high efficiency, complex electronics, medium bandwidth, but it's got a low immunity to noise. You know for yourself, if you walk around with your Wi-Fi at home, it's easily to lose the Wi-Fi because it's got a low immunity to interference or noise. Okay, so that's the summary of them. Something I wanted to point out now. No, let's leave it at that. Sorry. The thought has jumped. Okay, This is typically what the screen of a modern radio looks like that we use in amateur radio nowadays, unless we buy a museum piece that came with Jan van Riebeeck on one of the 3 ships. It gives me a signal strength indication of what my signal is. In this case, I know my mode of operation is lower sideband. I'm busy receiving signal, and my frequency is 7050 megahertz. It's all that I can get from the screen. And why I wanted to show you this, if you look at it carefully, remember what is the frequency range of audio? It is that we use in communications, not in your hi-fi room, in communications. It's typically 300 hertz to 3.3 kilohertz. We only use about 3 kilohertz of bandwidth of audio when we modulate voice. So you can see in the lower sideband here, there is a SSB signal that is coming through, but there's also a lot of other noise jumping there as well. But if you look carefully in this block, where my cursor is going, there is a lower sideband signal that is coming through on 7050 megahertz lower sideband, because the yellow line is my carrier frequency of 7050 megahertz. Okay. Next, error correction. 20, 30 years ago, amateur radio was more or less about voice communications, and you had the odd RTTY station that was using amateur radio on RTTY, which is things we'll still touch on when we do that lecture. But things have changed over time, and nowadays the most communication, especially on the HF bands, happening is not voice. It is voiceless communication. And the things that are becoming very popular is where guys are talking to each other with keyboard to keyboard. Now, the young generation, as I've learned over time, they've got all these games going, and they've got Discord, and they're busy chatting to each other away on Discord, left, right, and center, to kill and shoot and go mad. Amateur radio has moved a lot in the same direction, where a lot of comms is keyboard to keyboard. It's no longer voice. The problem is it's easy for the zeros and the ones in the data to go missing or get corrupted or disappear when we're busy talking with each other keyboard to keyboard. So one of the things we have to do in your lectures is something which they call error correction. It is typically used when we're transferring digital information from one PC to another PC, or one terminal to another terminal, by using radio waves. And the methods we use to fix this problem of losing information is using cyclic redundancy checks, CRCs, forward error correction checks, FECs, error correction codes, acknowledgements, and retransmission. Okay, and we're going to go through this bit by bit so that you understand. Because let's say there's 2 people in a room talking to each other and they can't hear each other, or the one person doesn't hear properly. He's going to say, please repeat that for me. Please repeat that for me. Please repeat that for me. Or he's going to move closer. Now, if we're busy talking with radios with each other, you can't move closer. And if I have to ask every time, please repeat, please repeat, please repeat, I'm doubling the amount of time it's taking for me to transfer data or information from one side to the other side. And that's why they've come up with error correction, is that on the fly, in real time, they can fix errors without asking for a repeat. Okay. So in basic summary, that's all that error correction does. It avoids a continuous repeat of data because the other side didn't receive it correctly. Now, the first basic one that you have to know that's in your manual is called CRC, cyclic redundancy checks. I have data. Okay, here's my data that I want to send. Let's say it's the word hello that I want to send to my buddy on the other side of the world. My software would take all the zeros in this case. Remember that the data is represented by zeros and ones, as I showed you with PSK and with FSK. It's represented by zeros and ones. So my software, and in this case, we both have to use the same software, or we have to use the same source code. I take all the zeros, I manipulate them with the divisor, and I get a checksum, a CRC. Okay. This divisor and this divisor, the manipulators, if you want to call them that, these manipulators or divisors are software specific. So let's say we both want to speak English, we would use the same divisor. It doesn't help if one wants to speak Afrikaans and one wants to speak English, because then the divisors will be different and they won't understand each other. So the divisor is something which is fixed in the software, and it would exist on both sides for the same software. Okay, then I've got my checksum, my CRC. I add it to the data, and I transmit it over radio waves by FSK or PSK or QAM, doesn't matter, one of those methods. I transfer it to the other side of the world. My receiver would pick it up, and it would split the data and the checksum, the CRC, from the data, and put the data through the divisor, and the answer should be 0 if everything was correct. Let's take an example. If there was 50 zeros on this side, and I received 50 zeros on this side, my result would be 0. So everything is fine. If my result is not 0, it means that my data got corrupted. Okay, sorry about that one. That's CRC. So I take my data, I split off all the zeros, I manipulate it, I get a checksum, a CRC. I transfer the CRC together with my data, I combine it, I send it to the other side of the world. I strip the data and the CRC from each other. I put it through the same divisor as the transmission side, and if I don't get any result, it means my data's integrity is perfect. It's 100%. Come on. Okay. If the data is not correct, and this is now where things start getting complicated. So all the CRC does, the CRC tells me that all the information that left the transmitter, all that information arrived correctly at the receive side. That's what my checksum, my CRC tells me. Whatever's left the transmitter has arrived on the receive side. If there's an error, I've now got to fix this error. And I can fix it by please saying, repeat for me, please send again, please send again, please send again, until my checksum check becomes 0 on the receive side. Or the other thing they do that makes it more intelligent is they have what they call forward error correction. And forward error correction, I would have my original data, and this original data is likely to have the CRC inside. I put it through a forward error correction encoder, and I get a certain amount of modified or manipulated data, which I transmit to the other side of the world. The other side of the world, I receive this bunch of manipulated, modified data from the receiver, and I put it through my forward error correction decoder. And now this is the interesting part. So if anything was wrong in the data, in other words, something got corrupted along the way, the forward error correction decoder would fix it. So it's got the intelligence or the ability to reconstruct the data within limits, obviously, but it's got the ability to reconstruct the original data and give it to me. So that I can see on my screen, let's say this side we type the words hello friend, on this side of the screen will appear hello friend, because the forward error correction decoder would fix any mistakes within limits that it can. And this can be done now without asking the transmitter, please repeat, please repeat, please repeat. It fixes it automatically on the fly without the transmitter even knowing. Okay. These forward error correction encoders and decoders, there were some clever dudes that lived many years ago, well before us. They came up with these methods in which you determine what the forward error correction data should look like. So if we go back here, so in other words, how do we package this information? How do we manipulate this information and package it? And on this side, how do we unmanipulate it and display it again? And this is done with what they call error correction codes. And the clever codes or the clever algorithms that they use to do that is called either Hamming codes or binary convolution codes, or the Reed-Solomon code, which is a very popular one for amateur use, by the way, and then the low density parity check code. A lot of our amateur software that does digital modes relies on the Reed-Solomon code. So it was clever guys that mathematically worked out years ago how to manipulate data and reconstruct it if there was an error. Okay. So let's just take a step back. Okay. So all the CRC does for me, it just tells me if the data that I received had a mistake in or not. Did I lose something? Did I corrupt something? Did something goes missing? Yeah, that's all it does. It tells me something is not kosher with what I received. That's all a CRC does. FEC has got the ability to fix a mistake. So if the CRC says there's a mistake in the data, the FEC decoder can fix that mistake and reconstruct the original data without asking for a repeat, which is wonderful because it saves you time. And then the way in which they do this fancy mathematical corrections, they use one of these codes: Hamming, binary, Reed-Solomon, or the low density parity method. Okay, I hope that makes sense if you see it in that perspective. The last two, which is not really part of those first three, but it's an important one, is whenever I send data from one side of the world to the other side of the world, there's always an acknowledgement coming back. Okay. Now the acknowledgement is could be just thank you, thank you, thank you, thank you. That's all the acknowledgement is in real life. It's not a long, timely process. So this thing doesn't keep on talking 1, 2, 3, 4 for an hour on end. It sends a block of information, a block of data. Okay. That block of data needs to travel to the other side. This side has done all the corrections. It fixed the errors in the data, and all it says to the other side, acknowledge I have received the data, and the other side would send the second block of data. If it doesn't receive an acknowledgement, if there's a timeout, it will resend that same data again until it gets an acknowledgement from the other side to say, yes, data received. Okay. You'll see it when you start playing with amateur software. It will keep on sending the same information over and over until it gets an acknowledgement from the other side. Okay. That's it. Modulation. Done. Dusted. Any questions? Nothing. Gee whiz. Okay. Hope it was all clear. Let's run through the questions. Let's see how good you're going to be in the exam. The process which alters the amplitude, phase, or frequency of a radio wave for the purposes of conveying information is known as
Modulation.
That's a freebie question.
That's a freebie question. I mean, you can't get it wrong. You can't get it wrong. Modulation. The process of extracting information contained in an RF or an IF signal is called
Also free.
Modulation. Yeah.
Demodulation. It's a freebie. The baseband signal is also known as the
Modulating
Carrying
signal.
signal.
Okay, I've got 3 answers. Think nicely. What is baseband mean?
It's the audio signal.
No, it's not the audio signal.
Is it not? Is it the carrier wave?
It's the carrier. Okay.
Okay.
So when I refer to baseband is always your carrier.
Okay.
Okay, it's not the modulation signal. So that could also be a nice freebie for you. Is yeah. Okay, 4. What does suppressing the carrier in an AM signal? Where we now? What does suppressing the carrier in an AM signal change the emission type to?
Double sideband.
Yeah, double sideband.
Double sideband, yeah. What is one advantage of double sideband suppressed carrier transmission over standard full carrier AM?
More efficient. More energy efficiency.
More energy efficient, yes. A Class C frequency amplifier stage is unsuitable for raising the frequency of an SSB signal because of?
I think it's distortion, isn't it?
Distortion.
Yes.
What is a Class C amplifier? If I think who did it? Louis did it with you. A Class C amplifier is effectively a switch. And a switch is not a very good amplifier for amplitude modulated signals. So it is distortion, yes. 7, what signal component appears in the center of an amplitude modulated transmitter's emitted bandwidth? Think of my frequency domain pictures. What signal component appears in the center of an amplitude modulated transmitter's emitted bandwidth?
That'll be the carrier.
The carrier, yes. 8, in a frequency modulated signal, deviations from the carrier frequency depends on?
The amplitude.
Amplitude, yes. What sideband frequencies will be generated by an AM transmitter having a carrier frequency of 7250 when it is modulated less than 100% by an 800 Hz pure sine wave? So how do we calculate this one?
Plus and minus 800 hertz.
Plus
So
or minus, yeah.
I get C. I think it's 7249.2.
Yes, it is 9C, yeah.
Yeah.
Yeah. So if they talk AM, remember it's got the upper and the lower sidebands, and they are symmetrical. They are a mirror from each other, and the mirror point is the carrier. So if it says 800 Hz pure sine wave, it means carrier plus 800 and carrier minus 800. That's a mirror from each other. Okay, the suppression of the carrier wave and one sideband in the transmission is known as?
It's single sideband.
Single sideband modulation, yes. What determines the bandwidth occupied by each group of sideband frequencies generated by a correctly operating AM transmitter?
Is it the audio frequencies used to modulate the transmitter?
Correct. Remember AM modulation? Lower and upper sideband is a mirror of each other, and it's dependent on the audio frequencies that I modulate with. Okay. By the way, I'm mulling about that other question. I think I made a mistake, but we'll come back to it now. The term narrowband FM modulation usually refers to a signal of
2.5 plus minus 2.5.
2.5. Yes. 75 kilohertz is typically wideband FM, which is used for radio stations in the FM band on 88 to 104, 106 megahertz. Okay, 13. The bandwidth of a speech quality AM transmission should not exceed
3.
Read it carefully. The bandwidth of a
That's 6.
speech quality AM transmission. What did we say is the frequency range we use for communications? 3 kilohertz roughly. Okay.
So it's 6 kilohertz.
So it's 6 kilohertz because the upper sideband and the lower sideband is a mirror of each other around the carrier. So if my modulating frequency is 3 kilohertz, I'm going to occupy 6 kilohertz of bandwidth. When the modulation signal reduces the amplitude of a modulated wave to 0 periodically, the modulation is
Overmodulated.
Mm-mm.
Oh, periodically. 100%.
100%. Remember, if you go back to those little graphs that I showed you on amplitude, I said if we get to 100% modulation, there's a little bit of a flat line in between the audio frequencies.
Oh, so if it's over 100%, then
it'll be a massive flat line. Yes.
Oh, okay. Thanks.
Yeah. The switching on and off of a transmitter to produce different lengths of carrier pulses for transmitting Morse code is called
Keying.
Yeah.
Keying. Yes. Keying. Last one, CW, SSB, FM, and AM are all types of.
I think that's also a freebie.
Yeah.
It is a freebie. Of course, it's a freebie.
Yeah.
Yeah. I just want to go to that one. I think I was wrong there. My apologies. My brain is not always with me. Where were we? You were right. Where is it? Where is it now?
Number 3, was it the modulating signal?
Yes. Baseband signal. Yeah, it's the modulating signal. My apologies. I was thinking something else. It is correct. It's the modulating one. Is the correct answer, not carrier. Baseband is modulating signal. Okay, I fixed that one for you. Yeah. Shift F5. Let's just capture this for the recording so that you have it available if you want to refer back to it. Mr. Yellers, all yours.
Thank you very much, Johan. I'm going to stop the recording.